Let's talk about valence bond theory for coordination compounds. Valence bond theory was put forward by Linus Pauling in 1931. And at the time, the objective of the theory was to explain bonding in main group elements, that is, your S and P block elements. So, the basic idea behind the theory was that if atom A and atom B were to form a covalent bond between them, their half-filled orbitals must overlap, like this. Now, this theory worked nicely to explain shape of molecules for main group elements, but it couldn't be applied directly or as it is to coordination complexes. And the reason is that the kind of bond that exists in coordination compounds is dative bond. You can also call it coordinate covalent bond. Now, what's special about this bond is that the electrons that are shared between the central metal ion and ligand, they're both donated by the ligand, and the central metal ion just accepts them. So for that, Linus suggested that for this kind of bond, the overlap that takes place between empty hybridized orbitals of central metal ion and filled orbitals of the ligand, like this. Let's see how this all works with the help of some examples. Our first example is hexacyanoferrate ion or ferricyanide. First, let's work out oxidation number of the central metal ion here. Let's say it's X plus 6 times minus 1 being the charge on cyanide ions, equals to minus 3. Minus 3 is the overall charge on the complex. Solve for X and you get X equals to plus 3. So the oxidation number on iron in this complex is plus 3. Iron, atomic number 26, has the configuration argon 3d6 4s2. If 3 electrons are to be removed from this atom, they'll be removed first from 4s and then from 3d. It's because 4s is the outermost orbital here. So removing 2 electrons from 4s and 1 from 3d leaves us with 3d5. So looking at the orbital diagram of Fe3+, we have a half-filled 3d orbital. Coordination number of this compound, of this complex, is 6, which means we need 6 empty orbitals. We have 4s, we have 4p, so that is 4. We also have access to 4d, but cyanide here is a strong field ligand, which means it can cause pairing of electrons, freeing up some 3d orbitals. So now situation or arrangement in 3d orbital of Fe3+ looks something like this. So we have two 3d orbitals which are freed up. We have 1 4s and 3 4p. So we have 6 empty orbitals. But consider this. 3d, 4s, 4p, they all have different shapes, different orientations, and even different energy levels. And when we see complex of iron with different ligands, 6 cyanide ligands, all these bonds are equivalent, which means that all the orbitals of iron used to make these bonds must also be equivalent. For that, 3D, 2 3D, 1 4s, and 3 4p orbitals will undergo hybridization to give 6 D2sp3 hybridized orbitals. Now 3d orbital would look like this, having the electrons of iron, and 6 D2sp3 hybridized orbitals will then arrange themselves around central metal ion in such a way so as to minimize repulsion, which gives us octahedral shape. Now these orbitals are ready to accept electrons from 6 cyanide ligands. Now there's some terminology we use with coordination complexes. Let's see. So this kind of complex which uses inner d orbitals. See, we have 3d orbitals and we have 4d orbitals. But in this complex, 3d orbitals were used for hybridization because of the strong field ligand which could cause pairing of electrons. So in such complexes, because 3d orbital or inner orbitals were used, we call them inner orbital complex. Spin of a complex is because of its unpaired electrons. And here, most of the electrons got paired up. So this kind of complex would also be called as low spin complex. Or in some books, you would find this term, spin paired complex. But there is one unpaired electron, which makes this complex a paramagnetic complex. Right? Now this was the situation when we have strong field ligand. Let's see what happens when the ligand is a weak field ligand. For that, let's consider this example. So here we have hexa-aqua ion 3 ion. Now, water here is a neutral ligand, a neutral molecule, which means it doesn't have any charge, which means the charge on the complex is the charge on the central metal ion. That means ion here is ion 3+. Now we have seen in the example before that ion 3+ has 3d5 arrangement. But water here is a weak field ligand, which means it will not cause pairing of electrons, which means ion would have to use its outer d orbitals for hybridization. So here 1,4s, 3,4p and 2,4d orbitals would be used for hybridization to give us 6 equivalent sp3d2 empty orbitals. Now these orbitals will arrange themselves in octahedral shape since the coordination number is 6. And then they will be ready to accept electrons from 6 ligands. 3d of course will have electrons of iron only. The charge on iron here is Fe3+. So here, this is the situation when the ligand is a weak field ligand. Now let's see what kind of complex is this. So here outer d orbital was used, so this would be an outer orbital complex. None of the electrons got paired up. That makes it a high spin or spin free complex. There are so many unpaired electrons, which makes it a paramagnetic complex. Now these were the situation when the complex had 6 coordination number. What about if the coordination number is 4? Let's see some examples of that. So our first example is tetrahydroxozincate ion. Let's work out the oxidation number of zinc here. Let's say it's X plus 4 times -1 being the charge on hydroxide ions equals to -2. Solve for X, you get X equals to +2. Now, zinc atomic number 30 has configuration argon 3d10 4s2. Zinc 2+ would have configuration argon 3d10. Now, 3d10 means that the 3d orbital is completely filled like this. Now, even if the ligand is strong field, it doesn't matter here because there's no space for pairing up of electrons. There is no unpaired electron. So right now, zinc would have to use its 4s and 4p for hybridization. So 4s, 4p hybridized to give us 4 equivalent sp3 hybridized orbitals. 3d orbital of zinc 2+ here would have electrons of zinc, and these sp3 hybridized orbitals will arrange themselves in space in tetrahedral shape and would then be ready to accept electrons from 4 hydroxide ions. Now, shape is tetrahedral. Spin, what do you think the spin would be? All the electrons are paired up, so it would be a low spin or spin paired complex. And again, since all the electrons are paired up, this would be a diamagnetic complex. Let's see one more of coordination number 4. It's slightly different than before. Now here, we have tetracyanonickelate ion. Let's work out the oxidation number of nickel. X plus 4 times -1 equals to -2. This gives us X to be +2. Oxidation number of nickel here is +2. Now, nickel Atomic number 28 has configuration argon 3d8 4s2. Nickel 2 plus would be argon 3d8. Orbital diagram of nickel would look like this: 1, 2, 3, 4, 5, 6, 7, 8. Now there is scope for pairing of electrons, and cyanide, we know from examples before, is a strong field ligand. That means it would cause pairing of electrons. That would free up one 3d orbital. So your nickel 2 plus ion would have 8 electrons of its own in 3d orbital, one of the 3d orbital, one 4s and two 4p orbitals would hybridize and give you 4 equivalent d2sp, sorry, it would be dsp2 orbitals, 4 equivalent dsp2 orbitals. 3d orbitals here would have electrons of nickel. 4 dsp2 hybridized orbitals would arrange themselves in space in square planar shape. That is the shape we get with hybridization dsp2. Now they are ready to accept electrons from 4 cyanide ligands. Now this complex, as you can see, is inner orbital complex because inner d orbital was used. We would call it a low spin complex because electrons got paired up, or spin paired complex. And again, since there is not even a single unpaired electron, this would be called as a diamagnetic complex. Thank you.